Welcome to E555 discussion 10. Today we'll give a brief introduction to Mininet and OpenFlow project. Mininet is a network emulation software allows you to launch the virtual network with switch hosts and SDN controller, all with one command and with one virtual machine. And it gives a great way to learn software-defined network and OpenFlow and the software-defined network controller and the software-defined network applications. And you can go mininet.org or GitHub Wiki to get the more details like installation or the tutorials. And if you are using x86 machine, it's very easy to install Mininet. Just install the pre-installed Mininet virtual machine image and import it into your virtualization system. It's very easy. But if you are using MacBook with Apple Silicon, it's a little bit complex. You should install the Ubuntu 20.04 system first and use sudo apt-get, install the Mininet, and check the Mininet version, use sudo -version, and check if you successfully install the Mininet, use sudo -3, use this command. And besides, it's like seems like VirtualBox stopped supporting for Apple Silicon, so you may want to try VMware, and you can sign up a free key for students. And firstly, let's introduce the default topology. Use the Mininet. We can use sudo mn to create a simple default topology in Mininet. And as you can see here, let's see, it can use sudo mn and adding a controller is a reference controller. It's a default controller if you just use sudo mn. And it can add two hosts, h1, h2. These two hosts, they are using the network namespace feature of Linux. Even they are in the same virtual machine, use same user code, running the same program, they are really like two different machines. You can access to one of them and run arbitrary program. So they isolated from each other. Let's see. Exit. Firstly, you SSH into your Mininet virtual machine and run sudo mn, and it will create a simple default network. As we talked before, you have the default controller host and the OpenFlow kernel switch, and you can see there are two links, and here is the topology. And here are some commands help you to test or do some experiment with your Mininet. First help, let's see. If you run help, it print out a lot of the command. You can see first nodes. It lists the node C0 means the controller, and H1 host 1, H2 host 2, S1 the kernel switch 1. And if you want more details, use dump commands. It will list every node with their detailed information. Here, like the interface and IP address and the PID of host 1, of course, same host 2. And the default reference switch, the kernel switch, you can see the loop address, loopback address, and interface 1, interface 2, and also the reference controller. And also you can use links to show all the links in your topology to check if there are any errors in your topology. And also you can use H1 ping H2 to see if they can contact each other. And here is one thing I want to mention. Maybe you can see that for the first packet, there is an extra delay on it. The time equal to 3.47 millisecond. And the remaining, there are just 0.0 millisecond. The extra delay is introduced by the communication between the switch and the controller, because it's the first packet. So when the switch receives the packet, receiver doesn't know what to do with this packet. He should ask the controller. So this delay is introduced by the communication between switch and the controller. And as you can see, the remaining, the later packets, they don't have that extra delay. And we will talk about the open flow, the delay later in detail. Also, you can use pin O to see if all the nodes they can connect with each other. H1 can pin H2, H2 can pin H1, and 0% drops. And also, you can test the bandwidth in your Mininet use perf. Here, wait a second. Yeah, and you can test the bandwidth between two nodes, means test the bandwidth for just one link, Yes. And also here you may see external H1. You may also use external H1 to SSH to H1 and to run code, do some tests in H1 or set a web server on H1. I haven't installed the external and the GUI dependence. So if you are using the Ubuntu system with UI, you may want to try external H1 to SSH into it and do some experiment. And also let's exit. And I will recommend that whenever you exit the topology, you sudo mn-c to do a cleanup to kill all the zombie process, which may prevent you from running a new clean topology. Okay. And okay, in this example, I will run SDN controller instead of run the reference controller. In the project, you are asked to write your customized controller. So we should so here let me show this example to run a remote SDN controller, remote controller. Let's go to pause and run the POX forwarding the L2 learning switch. This switch, this is an L2 learning switch. This is a combination with SDN controller and the L2 learning switch. Let's run this controller, and it says the controller is up. Let's do sudo -controller equal to remote. By doing this bump, you can see here remote controller, and here the information like the loopback address and port and PID representing the remote controller has connected to our topology. And let's do H1, pin H2 to test if the switch can connect to the controller. And yes, so in the project we should run our customized controller. Because by default the Mininet will run the just default controller. So let me see. Let's just stop this to verify the controller has connected to the topology. Let's just stop this controller and let's just H1 pin H2. You may see they lose the connection and there should be a timeout. But here is one interesting thing I want you guys to see. is that if we just restart the controller and we do H1 pin H2, and we just stop the controller quickly, and we rerun the pin action. Let's see. Oh, let's stop it and stop the controller and run the pin method. You may see there's still a connection. P1 still can pin, H1 still can pin H2, even though there's no controller running backend. So why this happened? Because even though there is no controller, the controller has already installed the rules, the routing rules in the layer 2 switch. The layer 2 switch cache the rules for maybe 10 seconds or 30 seconds. We can customize that. So because they cache the rules, so they, even though there's no controller, the H1 can still ping H2. But after several, maybe 10 seconds or 20 seconds, the rules are removed after timing out, so they cannot ping each other. We will talk about the rules and the timeout in detail later. And except we can customize the controller, we can customize the topology, and also Mininet provides a example topology in this directory, and let's see. Exit, and we should do sudo mn-c to do a cleanup, and just one thing. We should go to this directory to launch our customized topology. Sudo mn sudo custom topology. This topology here. And so here, this is a customized topology, and we have two hosts, two switches. By the way, in software-defined network, usually we call switches and routers. We call them switches. And we have two switches, and we have 3 links, and also we got the default controller because we haven't specified the SDN controller, and we use dump to see the details, and also we can use links to show all the links. So we successfully load a customized topology, and also I want to give some explanation about how to write this topology. For example, the left host, right host, left switch, right switch, they just names. You can name them whatever you want. But here in this self-add host method, you should follow this format, like H1, H2. H represent the host, S represent the switch or router, and you should add a unique integer followed by the H or S, the character. And for self-add link, you just add the name, like left host, right host here to add a link between them. And let's so when you do while doing your project, when you finish topology, you can use this tool to virtualize your topology to see if it's correct or not. It's sphere, which is this is online Mininet topology virtualization. First, you could use dump command to get all the details of your nodes and copy them and paste here. Paste the result Mininet dump here, paste here, and run links here to copy all the links in your topology and paste here, paste the result of Mininet links here, and run the graph. You will get the topology, two hosts, two switches, and three links between the connect them, and you can see the. I'm sorry. You can see the details about the host, the name, IP address, MAC address. I haven't configured the MAC address. You can configure the static MAC address to them in your customized topology. Yes, by doing this, you can verify your topology. Here also the switches here, and also here's another tool I recommend. Which is the T-Shark. T-Shark is the command line version of Wireshark, and it's a powerful tool. It can capture the packets, analyze the traffic, and it's useful to do troubleshooting while doing your project. And here are some commands: sudo apt-get install T-Shark to install it. And if you want to capture all the traffic, just run sudo T-Shark. Or you want to list all available network interfaces, use -d, or you want just capture packets for Ethernet 0 for this interface, just use -i is 0, or you want to catch packets for any interface, use -i any. But I recommend to add this node port 22 because you don't want to capture the packets for SSH. It will bother you to analyze the packet. And also, if you want to filter out the SMP packet, use -f. And also, the last two commands will just write the packets you captured into a file and read that file. Let me show some example. We still use this topology. Sudo -c to do a cleanup and run this default topology. And if we want to catch, because I already installed the T-Shark, so I just sudo T-Shark, and it start capturing and ping O. Wait a minute. Sorry, let's do it again. Let's specify any. As you can see, if you specify any, it's difficult to figure out which is the useful package, which is not. So I usually do not TCP port 20. And do ping again. Because I already do ping before, so there's no need to ask the controller what I should do for the SMP packet. So you can see they can ping each other from host 1 to host 2 for the pin request, and host 2 to host 1 pin reply. They can pin each other directly without connecting to the controller. Let me exit this. I want to show some OpenFlow packet. So let me restart this H1 pin H2. Let me stop capturing. Let's see, here are some beautiful OpenFlow packets here. Oh, also here are the ARP packets, because we run H1 pin H2, so H1 will send this who has the IP address of H2 tell H1, and because and send some OpenFlow packets. We will talk it later, and we will have the SMP request package, and also we will have the SMP request reply. Yes. And so T-Shark is a powerful tool, and I will show more details. So I will show more details about T-Shark in this part. Let me introduce OpenFlow protocol firstly. So the OpenFlow protocol is a standardized protocol for interacting with for the behaviors of switches from multiple vendors. This provides us a way to control the behavior of switch throughout our network dynamically and programmatically. So OpenFlow is a key protocol in many soft-defined network solutions. And we will use this topology. We have just one reference controller and OpenFlow kernel switch and 4 hosts. And I will set a HTTP server in H4, and I will do HTTP get from H1 to H4, and we will go through what happened with the in this process, especially to capture the overflow packet to see the procedure. Okay, first we should run this topology single for exit. See, we have this topology, and I use now. We have four hosts and a kernel overflow switch here. It has 4 interface and a reference controller here, and let's run run the T-Shark later. Then I will establish a simple HTTP server on H4. On port 80 and on backend. Sorry. And then we will start capture the packet use T-Shark. And use H1 get H4 to send a HTTP request get request to H4. And let's see, and stop capturing. We just skip the ARP packet, and we'll find, because HTTP request, the first packet in HTTP get request, the first packet should be the same packet, which SYN packet H1 sent to H4. So let's find the SYN packet here, and it's H1 sent to H4, and then the overflow packet in the later, which is overflow packet in and the overflow the modification and the overflow packet out. Then after this, okay, let me just check. After this, they can send the same message successfully, and then H4 will send H1 a SYN ACK packet back, and still we need to packet in, flow modification, and packet out. And after that, after the switch figure out what switch should do to this packet, then host 4 could send the SYN ACK message to host 1. Let me talk about this. Introduce this first. So while initializing a HTTP GET request, H1 will send H4 a SYN packet at first on port 80. But the switch receives that packet. The switch doesn't know what he should do for this packet. So switch will send a packet in message to controller to ask what the switch should do for this packet. The packet in message, it may encapsulate the Intel SYN packet, or it can just only contain some header and the buffer ID of the SYN packet. Because the SYN packet is buffered in the switch S1, and the switch S1 could just send the Intel SYN packet encapsulated in a packet in message to the controller, or it can just send the reference the buffer ID in the packet in message and send to the controller. Then the controller will send a packet out message to the switch, or it will send the flow modification message to the controller, to the switch. First, let's see the packet out. The packet out message, it contains two things. The first thing is the Intel SYN packet, or the buffer ID of the SYN packet. And the second thing is the action, is what the switch should do to the SYN packet. So if the packet out contains the Intel, if the packet out message just contain the buffer ID, let's say 250 of the SYN packet, the switch receive the packet out message. The switch will release the buffer at the buffer ID equal to 250 to release the SYN message and do this action forward to port 4. So by doing this, switch know what to do to his buffer and do this action. Just forward the packet in buffer ID equal to 250 and forward that packet to port 4, which connects to the host 4. Or the controller could send a flow modification message to switch. Flow modification message contains six things. The first thing is the match and the mask, which means the controller will tell the switch if any future packet coming from the MAC and IP address of H1 and the two IP and MAC address of H4, if any future packets match this MAC and IP address, the MAC and the IP source and destination destination address, the switch will do this action. Forward to port 4. If any future packets matching this IP address or MAC address will do this action. And also, it will if the buffer ID is optional. If the flow modification message contains this buffer ID equal to 250, it will tell switch to release the first packet in your buffer, which is the SYN packet. Because SYN packet is the first packet in the HTTP GET request, so the switch buffered the SYN packet, and the flow modification message will tell the switch to release this SYN packet, whose buffer ID equal to 250, and do this action, forward to port 4. So this buffer ID equal to 250 are only useful for the first packet, because in the future, the later similar packet, they are not they don't need to wait the response from the controller. They can be forwarded directly to H4 because the rules are already installed. And also we can see there are two timeouts. The first one is idle timeout. The second one is hard timeout. The idle timeout means actually this two timeout is related to the interesting thing I showed before, which is there's no controller running on the running backend, but H1 still can pin H4 because of the timeout. The idle timeout means if there is no active future similar packet from H1 to H4, the rule will be removed after 20 seconds. So if there is active similar packet from H1 to H4 within 20 seconds, so the rule will not be removed. But there is another timeout, hard timeout, which means after 60 seconds, remove the rules, remove the flow entry. So it's the hard timeout. And of course, here is an action to tell switch how to deal with the packet. And also here's an important parameter, which is the priority. For example, there may be multiple flow entry for one packet in your flow table. But the flow entry with the highest priority will be used. The remaining the lower priority, they will be ignored. So if you receive the packet, there are multiple flow entry for this packet. You just use the flow entry with the highest priority. The others you just ignore the other flow entry. And by doing this, by this flow modification message, the controller installed the flow entry in the switch. So the future packets, they can be routed directly from H1 to H4. And so the SYN packet and the SYN packet, this is also the first SYN packet. It is released from the buffer of the switch, and this SYN packet is routed to the H4. Then after this, H4 will reply a SYN ACK packet to H1. So at this time, this SYN ACK packet will be buffered in the switch, because switch doesn't know what to do with this packet, because the switch, even though switch know how to deal with the packet from H1 to H4 for the HTTP packet port 80, but S1 doesn't have the table entry for the SYN ACK packet from H4 to H1, and so this situation is named table missing, the flow entry table missing. So if S1 cannot find a solution for this SYN ACK packet, S1 will ask the controller to instruct switch 1 how to do. And this situation named table missing. So in the same SOS, we'll send a packet in message to the controller, and also this packet in message will encapsulate the Intel SYNAC message, or just encapsulate some headers and the buffer ID of this SYNAC message, which is 251. And controller will figure out what to do with this SYNAC message and send a packet out message to the switch, which also may contain the Intel SYNAC packet, or just contain the buffer ID. And also the packet out message will contain the other parameter, which is the action to instruct switch S1 forward the SYNAC message to port 1, which connects to H1 here. And also the controller may send a flow modification message, which is similar with before, just containing the first parameter match and mask, which contains the source destination, MAC, and IP address. You should match this address, then you can use that flow entry. And also, here's the buffer ID equal to 251, which means release the SYNAC message buffered in the switch whose buffer ID equal to 251. And also here are 2 timeouts and the action for the flow entry, and also the priority. So after receiving the flow modification message, switch will install the rules in switch. So switch will know what to do with the SYNAC message and forward it to port 1 to H1. So after these this sending and sending back and the response, the switch will know what to do with the future similar packets from H1 to H4 or H4 to H1. And in the future packets, the packets can be routed directly without sending to the controller. So the latency will be lower than the future packet. The latency of the future packet will be lower than the first one. And also the HTTP reply, these packets are routed directly. And okay, let's use T-Shock to discover more details. Just run the T-Shock to capture the packet and stop capturing, and let me find the first SYN packet. Where is the first SYN packet? First the SYN packet, and the packet in encapsulate the SYN packet and send it from the switch to the controller, and the flow modification sent by the controller and to switch, and also packet out and sent by the controller and to switch. By doing this, switch will know what to do with this packet. So H1 to H4, you can see H1 can reach out H4 successfully, and H4 will send back a SYNAC packet, and also packet in and a flow modification and a packet out. And after this, H4 knows the switch knows what to do with the SYNAC packet. And let's see. the last thing, I want to show more details about the packet in T#. We use -v to show the details. Of capturing, and it's difficult to find, but it's okay. Pass not equal to pass equal reply. Oh, hey, here. So we just jump the ARP packet and jump the first SYN packet. Let's take a look at the packet in message directly. So here, let's see, it's frame 6, and the type is open flow packet in message, and you can find the buffer ID here, which is here. So this packet in message doesn't encapsulate the Intel SIM packet. It just it just contains the buffer ID of that SIM packet, as you can see here, and it will figure out the IP address is from let's see. Oh, I'm sorry. I should also show the SYN packet. Not here. Because I want to show there is a table missing signal in the SYN packet. This should be easier to find. I'm sorry. Frame 1, and let's check. Here is a SYN packet, and we will find there is a table missing here. You can see the same message is sent by host 1 and to the host 4, and I will upload this on Piazza and also upload the recording on the on Blackboard. So I'm sorry for this. By the way, are you starting your final project or not? E555? Okay, it's okay. The project, if you're not familiar with Python, it's totally okay, because what you should do is just use Python API. It's just core API to do these doable. And there's a lot of you're very welcome to ask questions on Piazza for the final project. If you didn't figure out some problem, maybe 30 minutes or 1 hour, you just raise your problem.
This is the complementary part of the discussion 10. I will use this controller for the topology. As you can see, the controller is connected, and I will initialize a HTTP server on host 4, and then I will send the HTTP GET request from H1 to H4, and to go through the details in the OpenFlow package. And also, I should use T# to capture the OpenFlow package. Okay, let's start. And here is the segments package we captured. Let's use search OpenFlow. Here you can see here's the OpenFlow package in package. And you can find the buffer ID here. And here is a reason no matching flow. Table means flow entry. This is because after receiving the same message, the switch will look up the table and find a matching flow entry, but the switch cannot find a matching flow entry because the same packet is the first packet. So this called table missing. And table missing will automatically instruct the switch to send a packet to the controller to get the knowledge about how to deal with the same packet and deal with the future similar packet. So you can find the wizard table missing here. Also, you will find some headers of the same packet in the packet, like the source destination MAC address, IP address. Let's go to the next overflow packet. And here you can see here is an overflow modification packet. And in this packet, you will find also the source destination MAC address and the source destination IP address, and also the port number, source destination port number. These are the headers of the SIM packet. And also you can find the idle timeout equal to 10, hard timeout equal to 30, and priority, and the buffer ID, which means this modification flow modification packet only contain buffer ID to reference the packet stored in the buffer of the switch. Yeah, also you can see here is the OpenFlow packet out packet, and the packet out packet contains the buffer ID and contains the action, like here output to switch point 0. So in this controller, it just combined flow modification packet and packet out packet, combine them into one packet. Then I guess this is the reason why you cannot find the actions field in the flow modification packet. Of course, you can find some headers of the same packet in the packet out message, like the source destination MAC and IP address, and the source destination port, and so on and so forth. So, so this is all the content I prepared for discussion 10. And for your project, you are very welcome to post question on Piazza or come to office hour. And good luck to your project.